Section 3.5, you have done a little bit of this section in the last 2 or maybe even 3 sections already, where you're using the information about graphs being increasing or decreasing, asymptotes, intercepts, and so forth. Are you guys good?
Yeah, sure.
Okay. To actually graph some kind of a function. And then at the end, we've always gone back and sort of checked that, make sure that the calculator is giving us the same kind of a graph that we were getting by hand. So this is going to formalize a lot of what we've already been doing, more than actually create something new. All right, so we're going to talk about how we go about graphing or curve sketching by hand. And there are 5 different steps that we're going to go through. They don't all happen on all problems, okay? So like the first one, the domain, that one's going to happen on everything. We want to consider whether a graph has certain values that in the domain that don't work or that are not in the domain, like certain x values that you can't plug in. In particular, that happens for rational functions, right, where you got denominators. Happens for square roots sometimes. So that's domain. The second one's vertical and horizontal asymptotes. That doesn't always happen on a graph, right? The graph of sine, it doesn't have a vertical or horizontal asymptote. Polynomials, they don't have that either. So this one's one of those steps that sometimes happens and sometimes doesn't. When it does happen, we want to remember how we find those asymptotes. And we've been doing this throughout the semester at different points. We find vertical asymptotes by looking where denominators are equal to 0. Excuse me. And then we have the horizontal asymptotes with the 3 cases, whether the degrees match, whether 1 degree on top is greater or the degree on bottom is greater. So those are those 3 cases. Step 3, intercepts. These are the places where they cross the x or y axis. Sometimes the graph doesn't have intercepts. The graph of y equal 1 over x, for example. It doesn't have any intercepts. So it doesn't always have intercepts, but we usually have intercepts. It's more common to have them than not to have them. And the way that we find them is by letting one variable equal 0 and solving for the other one. Okay, so intercepts are something we're going to find. And then the last 2 pieces of information are the pieces of information related directly to calculus. First derivatives and second derivatives. All right, so on step number 4, it says the first derivative information. So it says to take a look at where the first derivative is increasing, or where it's positive, means the graph is increasing, or where it is negative, in which case the graph is decreasing. So if we find the first derivative, and we set it equal to 0 and solve, right, that gives us critical points. And then we did that sign chart, that's one way we did it, where we tested the intervals in between those particular critical points, and made determinations about whether we have maximums or minimums at those critical points. What we did in the last section is we used the second derivative to make that determination instead of the first derivative with the sign chart. We actually tested the critical points inside of the second derivative. And you can do it from that perspective as well to decide whether or not you have max or min. The last one is about concavity. It's actually using the second derivative. So a graph can be increasing and concave up, or it can be increasing and concave down. And that graph looks quite different. So if it's increasing and concave up, it looks something like this. And if it's increasing and concave down, it looks something like this. Right? They're both increasing, but the concavity is different. So the graph ends up looking different. So we actually determine concavity issues based on the second derivative. If the second derivative is positive, it's concave up. And if the second derivative is negative, it's concave down. And then, of course, if the second derivative is 0, it is a place where it's changing concavity, and we call that an inflection point. All right, everything that I've said so far is stuff you know. We've done all of it. It's just put in this nice, neat little package of 5 steps. That's all it is. Nothing of this is new. So we're going to actually use all of this combined together now to actually go ahead and graph some functions. So here's our first one. It says to graph the function and completely discuss the graph. So when it says something like completely discuss the graph, it's talking about those 5 things. You're going to check to see what's the domain. You're going to find out if are there asymptotes. What's going on with those intercepts? Tell me what the derivative is and how that information is useful. Tell me what the second derivative is and the same thing. Okay? So when it says completely discuss the graph, if you use your calculator and sketch me a graph, that's really not going to get you any points. You didn't do anything that's actually part of calculus. So that's what this is referring to. All right, so let's start with the first step, which was domain. What do you know about domain for rational functions? Yeah, the denominator cannot equal 0, right? So at what x value here Well, the denominator equals 0. So my whole denominator, x cubed equals 0. That happens when x is equal to 0. So this cannot equal 0, so x cannot equal 0. So now we've sort of stated the domain in a negative fashion here. We've said what x can't be. Let's say what x can be. What does it mean the domain actually is? Very good. So we find the domain oftentimes in sort of a negative fashion, asking ourselves what can it not be. But we want to state the domain in a positive fashion, what can it be? So here's our domain. Step 2 was about asymptotes, and we have them here, don't we? All right, so we have two types of asymptotes. The first one is vertical. When do we have a vertical asymptote? When what equals 0? Which part? The denominator, right. So if the denominator is equal to 0, which we already did that, right? Then we have a vertical asymptote. So at what x value do we actually have a vertical asymptote? X equals 0. And remember, with asymptotes, these are lines, so they need to say either x equals or y equals. This is not vertical asymptote 0, it's vertical asymptote x equals 0. Horizontal asymptote, how do we determine that? Right, so we're looking at the degrees. It's all about degree. And in this one, Cooper's right. The degree on the bottom is bigger, right? So since the degree on bottom is bigger, we actually have a horizontal asymptote that's y equals 0. And again, y equals not just 0. That's step 2. Step 3 is about intercepts. In particular, we're looking for two intercepts, and they may or may not exist, okay? We're looking for an x-intercept and a y-intercept. So I'm just going to go alphabetical order. X-intercept. How do I find what an x-intercept, where an x-intercept would be located? What do I have to do? We let y equal to 0, right? So we're going to set y equal to 0. So where does y equal 0? Well, this is 0 equals x minus 4 over x cubed. Now technically, well, let me just say it this way. What could I do next to solve this? Sure. Multiply by x cubed on both sides. What happens when I do that? It goes away. And the reason is because technically the only way this is going to equal 0 is if the numerator is equal to 0, right? That's what I was about to say earlier. So where is the numerator actually equal to 0 here? 4. So my x-intercept is at x equals 4, y equals 0. Remember, an intercept is a point, xy ordered pair, right? Not just x equal 4. I want the ordered pair for it. So that's my x-intercept. Let's do y-intercept next. So if my x-intercept is when y equals 0, then my y-intercept is when x is equal to 0. And what happens on this one when we let x equal to 0? It doesn't exist, right? And the problem is the 0 in the denominator, right? So this can't work, so there is no y-intercept. Now, pause for a moment and think with me. That makes sense. Why does it make sense that there's no y-intercept? There's an asymptote there. Yeah, there's an asymptote there. So that's a reasonable thing to happen in this particular problem. All right, step 4. What was step 4? It was about first derivatives, right? It's really about increasing and decreasing graphs, but we find it by finding the first derivative equal to 0. So our information that we're looking for now is about increasing, where the graph is increasing and decreasing. And we find that by finding the first derivative and setting equal to, well, finding the first derivative. Let me just stop with that. All right, so let's find our first derivative, f prime of x. All right, so as we find this, we're going to have to use what rule? Quotient rule. We could get away with not using the quotient rule by simplifying and dividing each of the parts by x cubed. We could do that. We talked about that briefly last time. But we also can just use the quotient rule, which works fine here as well. So let's go with the quotient rule since that's what you guys saw. Tell me what I'm going to write down. Good. Times 1. And? Yeah, what would x cubed to the second actually be? Yeah, it'll actually be x to the sixth. All right, so we're going to simplify this. It could be worse, right? There's a fair bit going on, but it could be worse. So the first one is x cubed. And then I have minus 3x cubed. Agreed? Yeah. And then do I have minus or plus next? It's plus. How much? 12x squared. Good, and my denominator, as we discussed before, is now x to the sixth. What do you notice about that denominator being x to the sixth in the numerator, however? Yeah, there's stuff that we can simplify, right? Everything has at least two x's in it. I don't mean 2x, but it has x squared in it, right? So we can reduce this right off the bat, and that's the first thing we probably want to do, is to recognize, in fact, let me also combine these at the same time. These two right here have x cubed in them, right? So x cubed minus 3x cubed would be minus 2 or negative 2x squared, or x cubed. Let me do that before we actually reduce the x's. Okay, now let's reduce the x's. So we have negative 2x plus 12 over x to the fourth. Does that look good? Okay, we've got the derivative. What are we supposed to do with it? Set it equal to 0, which means the numerator is equal to 0. Very good. Okay, so I'm going to take this. We're going to go on to the next screen and use some more space over there. Okay, so Mackenzie said this means that the numerator is really equal to 0. What in the world, what value do we get for x for this to be equal to 0? 6, that's right. So x is 6. Does that look good? Okay, I have two choices of what I can do next. Somebody tell me one of them. I can do a number line. I can set up a sign chart. Does anybody know another thing I could do? This is last section, 3-4. I could do my second derivative and evaluate it at this point, right? That's another possibility. I'm going to do the number line because it's going to give me more information, because I really don't care just is it a max or a min. I really want to know what's happening on the whole graph in terms of increasing, decreasing. So for the purpose of what I'm needing it for, a number line is a little bit more practical right here. It's just going to provide us with more information. Now, I'm going to have a 6 on the number line, but there's something else I need on my number line as well. 0. Why do I need 0 on my number line? There's a vertical asymptote there. In particular, in terms of the derivative, it's where the denominator is equal to 0 in my derivative as well, which means it's where the derivative doesn't exist. Now, we know it doesn't exist because it's an asymptote, but asymptotes are also locations where the graph can change from increasing to decreasing or vice versa, right? So I do need that represented on this sign chart. So I will actually have 3 regions of this graph that I need to test. Tell me a value you'd like to test before 0. Negative 1. Between 0 and 6? 1. And after 6? 7. Somebody said 2, I think, but 7 is probably what we want, not 2, right? Okay, just checking. All right, so we'll test to 7. All right, so we've got my 3 values, which is great. And then what do I test them in? The first derivative, right. The first derivative is what gives us the information that we're looking for, increasing or decreasing. So we're going to test this, excuse me, each of these, I'll write it down here, into the first derivative. So we're going to find f prime of negative 1, f prime of 1, and f prime of 7. And I care about the sign. So test each of those, if you would. We're going to figure out what we have. Do we have positives or negatives? Take just a couple seconds, maybe longer than a couple seconds, maybe a minute or so. Plug each one of those in.
Can I see the derivative again?
Over here, the negative 2x one right there.
Yeah, it's plus 12.
Yep. What was that, Cooper? You got a negative 1 to be negative? Did anybody else have negative there? Positive?
Positive.
You have positive, positive, negative, like that? I'm seeing heads shake, several of them, so I think that that's probably what you're all getting. Yeah? Okay, great. What does that tell us? I mean, we know what happens at 0. There's an asymptote. What does that tell us happens at 6? There's a max, because this is increasing and then it's decreasing, right? So we have a max right here. So let's just write down what this sign chart actually tells us. It tells us a lot of things. It tells us that our graph is increasing in a couple of locations. It's increasing from negative infinity to 0. It's also increasing from 0 to 6, right? Because those were both positives. It tells us that it's decreasing from 6 to infinity. And it tells us that we have a maximum at the x value of 6. But I'm going to be graphing this, so finding the y value here makes a lot of sense because I'm going to be putting it on a graph, right? How am I going to figure out what y value goes with x equals 6? Put it in the original function. So that was over here. So I need to put in 6 minus 4 over 6 cubed. And if you'd like to give me a decimal or a decimal approximation, that makes sense because we're going to actually have to plot it somewhere. So that'd be all right. What do we get for a decimal or a decimal approximation for this? Can you say it a little bit louder for me, Josh? 0.009, something like that.
Yeah.
Okay, so it's almost 0, actually, right? It's going to be very, very close to the x-axis. Okay, this was step 4. Step 5 is what? About concavity, right? Our issue on step 5 talks about concavity. And how do we find things about concavity? Second derivatives. So we need to find the second derivative. All right, so my first derivative, I don't have it all recorded over here. But my first derivative, reduced form, is this value at the bottom right here. It's negative 2x plus 12 over x to the 4th. So that's what we're going to be using as we find our second derivative, is that reduced form. It'll be easier to work with a reduced form. So we will find our second derivative. So what do I get? How do I start? Thank you. X to the 4th. I need the derivative of the top. What's the derivative of the numerator? Negative 2. Okay. Minus. Now what? 4x cubed. Okay, the derivative of the denominator. Times. I think it's negative 2x, right? Yeah, negative 2x plus 12. Over what? X to the 8th. It'd be x to the 4th squared, which is x to the 8th. All right, we simplify cleanup just like we did in the last step, or the last step 4 of this problem, I should say. So this is negative 2x to the 4th. Then I have plus 8x to the 4th. And then minus what? 48x to the 3rd. All over x to the 8th. The first two pieces combine. So how many x to the 4th do I really have? 6. X to the 4th minus 48 x cubed over x to the 8th. Can I simplify? One more time. What can I do to simplify here? Yeah, basically I'm going to reduce each of them by dividing by x to the 3rd power, or an x to the 3rd and x to the power of 3. So this will give me 6x minus 48 over x to the 5th, right? X to the 8th divided by x to the 3rd would be x to the 5th. Well, what do I do next? Yeah, I set it equal to 0. And if I set the whole thing equal to 0, what does that really mean? It means the numerator is equal to 0. And at what x value would that be? It's at 8. So I'm going to do another sign chart. But the sign chart needs to include 8 this time, not 6. But it also still includes 0. Because again, the denominator equaling 0 means that I have a location where the second derivative does not exist. If it doesn't exist, it means it could change concavity there. And it is an asymptote, we know that as well. So we're going to test a value in each of those intervals. I think we can still use our -1 and our 1 from before. But how about we use maybe like 10 instead of the 7, since that one wouldn't be in our area, our region anymore. All right, I'm going to test these values where? In the second derivative, right? So I'm going to find f double prime of -1, f double prime of 1, and f double prime of 10. All right, what happens at -1? I get a positive. We'll talk about what it means in a second. What happens at +1? A negative. And what happens at 10? Positive. Okay, so this doesn't tell us about increasing, decreasing anymore, right? It tells us about concavity. So what in the world does a positive second derivative value tell you about the graph? It's concave up, right. So right here, we're concave up. And the negative tells us that we are concave down. And of course, we have a positive over here as well, then that's concave up. So I'm going to write my intervals much like I did on the last problem, except that I'm out of space. Let me actually write them over here. I can just write them over here with the others over here. I actually know that the graph is concave up. Where? -infinity to 0, and then also again from 8 to infinity, right? And then it's concave down, where? 0 to 8. So this is, what we've done so far is basically the second half of the direction. We have completely discussed the graph. That's what we've done. Now we're going to use all of those discussion pieces that we've arrived at to actually plot them on a graph and see what it looks like. We'll see if I have more space. I don't. Of course I don't. Let's do it here. And I can do that. All right, so here's my graph. There are some important values on my graph. Somebody tell me some of the important values that I might want to mark on my XY axis here. I want to do... What values have been important that I found in my complete discussion of the graph? What X values? 0 is one of them. What else? My intercepts. So I had something happening at what? 4? All right, so we're going to have 4 here. I'm going to mark that, 4. What other X values were important? 8 and 6. So I'm just going to label them because I know I'm going to need them in a little bit, 4, 8, and 6. You could obviously label other points on here too, but those I'm going to need to reference back to. All right, so let's just go down our list. Our first piece of information about the domain, that's not values that we're actually going to see on the graph. And we are going to see them, but we don't need to graph them right away. That doesn't give us enough information to do anything. But the second piece of information does. It was about vertical and horizontal asymptotes. So what is my vertical asymptote? 0. What equals 0? X equals 0. So I need to actually have a vertical asymptote where on this graph? Where is x equals 0, in other words? The y-axis. So my y-axis, I think it might have been better to do that a little bit bolder, but it should have a dotted line, right? You need a dotted line representing that you've got that horizontal or vertical asymptote here at x equals 0. What else do you have an asymptote at? Y equals 0. It's a horizontal one, right? Okay, so we're going to do a horizontal asymptote on the on the x-axis. Okay, so along the x-axis, I made it a little bit bigger this time. I've got this one. So this one is y equals 0. There's my asymptotes. The next thing was intercepts. I only had one. What was one of my intercepts? 4, 0. And we might feel a little bit awkward about plotting that particular point because why? There's an asymptote there. Well, we mentioned this last time. Asymptotes really don't tell us about specific values that are happening in the middle of our graph, the horizontal asymptotes. They tell us about the end behavior of the graphs. So we draw the line y equals 0 as though it sort of extends the entire graph, but it's only acting like an asymptote on the ends of the graph. So it's okay that we're crossing it in the middle. So that's not a concern. It feels like it should be, but it really isn't. All right, step 4 talks about increasing, decreasing, and what? What else piece of information do we get on step 4? Max, and that's what I'm going to plot next. Where did I have a maximum value? At 6 and almost 0, slightly above the x-axis, right? So it's not going to be a super accurate graph, but I do want to represent that it's a value slightly above the x-axis at 6. Okay. The other thing that I'm being told in the second piece of information is about concavity. So I need to use, I'm sorry, not concavity, increasing, decreasing, and then in step 5 about concavity. I need to use the informations from increasing, decreasing, concavity, and asymptotes all at the same time. So let's take a look at moving from the graph from left to right. Both pieces of information over here on the increasing, decreasing had something, increasing, decreasing, and concavity had something to do with what happens between negative infinity and 0. What does it tell me is happening between negative infinity and 0? Here and here. And concave up. Okay, so I need to have my graph be both increasing and concave up between negative infinity and 0. So what's that going to look like for it to be increasing and concave up? Like this, right? Okay, so my graph will look something like this over here. That is increasing and it is concave up, happening between negative infinity and 0. All right, the next piece of information is broken up by saying that I'm doing something between 0 and 4, or maybe 6, because that's actually the first location where I have differences of what's going on over here. What happens between 0 and 6? It's increasing and concave down. Now, I know the concave down goes all the way till 8, but it is concave down. So it needs to be increasing and concave down from 0 till 6. So what would that look like with this graph to be increasing and concave down? It's going to be near the x-axis, not x-axis, but the x equals 0 line at the beginning, so over here, right? And then it's got to actually cross through 4 and 6's values. So it's going to look like something like this. And we know after 6 what has to happen to the graph. It has to go down because that's a relative maximum. That's what we had found out. It needs to go down. So what's happening between 6 and 8 over here on these pieces of information? It's decreasing, right? And what? And concave up. Down. Which one is it? Oh, did I have my... Hang on. Yeah, it's concave down, right? Am I reading it right? Yeah. Between 0 to 8, there it is. Sorry, it's not on my screen where I'm seeing it, but you guys are. Between 0 and 8, it's concave down. So it still needs to be concave down. So it will look, I don't know if you will, parabola-like, right? Between 6 and 8. It's going downhill. But it's not going to cross the x-axis, is it? How do I know? There's not another x-intercept, so you can't go down very far. It's a very, very gradual decline. What happens to change things at 8? What's going on after 8? It's concave up and what? Still decreasing. So it's going to be really difficult because the graph's so tiny in this area of the graph. But at this value, let me actually sketch this in here differently, of 8, it has to be coming down like this. I mean, we know it has to do this on the end of the graph anyway because it's an asymptote. But at 8, it should look like there's an inflection point because the concavity changed. It should look, at this point, before it like we're concave down, and after it like it's concave up. It's hard to draw because it's so close already to the x-axis, but that's the image that we should be getting. All right, so pause for a second, put this in your calculator, graph it, and make sure that this is the overall image that your calculator gives you. Make sure you've got like a standard viewing window, -10 to 10 kind of thing going on. That looks reasonable for these values. Yeah. Above the x-axis, is that happening on you guys as well? Let's make our y-min and y-max really tight around there. Like, let's maybe go from -1 to 1 and see if we can see it. So keep your x values to go from -10 to 10, but let's make your y values go from -1 to 1, just to see if we can see that. It's going to be hard to see, right, because as we made note of before, they're really tiny numbers. I mean, like, that maximum is at a y value of 0.009. So yours worked. Did everybody else see that it does, in fact, cross a little bit? What did you end up using, Phil?
I used 0.05.
Okay, 0.05 is what I tell you. So let's try that for your maximum on y, 0.05. This is good because this actually makes you think, now did I do it right? Because I didn't see the graph and it didn't look like it went above the x-axis, but it really did, ever so slightly, right? Is that good, Sam? The y-min and y-max we changed to -0.05 and positive 0.05. I think you'll see it then. But now you can see also why it was hard for us to graph it, right? Because those are just such slight values that are bigger than the x-axis actually is. All right, let's try another one. I don't think this one's a rational one. No. All right, on this one we have a square root graph. We're going to go through all the same things to discuss the graph that we did before. What is the first thing we're going to discuss? Domain. This is actually really helpful on this one. It almost feels unnecessary on the last one because we have so much other information. But this is a really useful piece of information on this one. What happens with domain and square root graphs? Yeah, we need values from the square root, right, that have to do with things about 0. I mean, there's something about 0. It's not exactly that it can't equal 0, though, like it is with denominators. So what do I have to do? What has to be greater than 0? What's under the square root? Yeah, not just x, but in our case, this one is the 2x minus 1, right? Everything underneath that radical needs to be greater than or equal to 0. And the reason for that is why? Right, square root of negative numbers are imaginary numbers, and we're working in the real number system for calculus. Okay, you can do calculus in the complex number system, but that's not our goal today. So we are going to let this have 2x minus 1 greater than or equal to 0. So what does this simplify to? X what? Greater than or equal to 1/2, right? So my domain is that this goes from 1/2, and it is a bracket there. It actually equals the 1/2 to infinity. That's my domain. So I'm going to have values here, but the values I have will not occur on the left-hand side of the graph at all. No negative x values at all. And not even some of the positive x values aren't going to be in there too. All right, second one, asymptotes. What can you tell me? Somebody say it so we can move on. What? What? There aren't any, right? Asymptotes are happening when we have rational functions. There's some trig functions where they happen with as well, like tangent and stuff like that. But there aren't any. There are no asymptotes on a square root graph. Don't just skip over it and not write it down, though, because then I wonder whether or not you actually thought through that particular step. So say there's none.
We know that, like, f of x can't be 0. It can be, like...
That's true, but that doesn't make it an asymptote. Just because it can't have a value doesn't make it an asymptote. You're right about that, but it doesn't make it an asymptote just because it can't have a specific value. Yeah. What was the third step? Intercepts. We have two types. We have the X-intercept. We have the Y-intercept. So let's start with X-intercept. What do we do to find X-intercept? Yeah, you said Y equal to 0. So Y equals to 0 means that I have 0 equals the square root of 2x minus 1. Square both sides. And we end up getting x equal to 1/2. Very good. So the ordered pair would be 1/2, 0, right? Because we let y equal 0. So that's my x-intercept. What about y-intercept? It doesn't exist. Why not? Right. I get a negative under the radical. It's not in the domain. There is none. That's not number 4. I don't know why I labeled that 4. Sorry. Now we're ready to do 4. What information does step 4 give me about this graph? Increasing, decreasing. We get it from the first derivative. Very good. So we're going to take our first derivative of our function. So we need the derivative of 2x minus 1, and it would be more helpful for that to be written as 2x minus 1 to the 1/2 instead of the square root. Right? So somebody tell me what I'm going to do. 1/2. Good. 2x minus 1 to the negative 1/2 times 2. And we're done, right? And nice things happen. What happens? 1/2 and the 2 cancel. How would I rewrite this? One over the square root of 2x minus 1. So that's my derivative. So now what? What do I do with that piece of information? Okay, so if I set this equal to 0, what do we find out? It doesn't equal 0, right? I mean, the numerator does not equal 0, so I don't actually have this able to be equal to 0. I do still have the denominator have the ability that the denominator could be equal to 0, and that would cause a problem here, right? So where does my denominator equal to 0? Yeah, it's that 1/2 value that was important to us a minute ago anyway. So we're going to have x equal to 1/2. What happens on the left-hand side of 1/2? It doesn't exist, right? These values on the left-hand side are not in my domain. Agreed? Yeah, they're not there. They are not in my domain. So I can't test something on the left-hand side of 1/2. I still can test something on the right-hand side of 1/2, though. So give me a nice value to test on the right-hand side. 1, I like 1 too. So we'll test the number 1. And what will we test it in? The derivative. So what is f prime of 1 going to be? Did you have it? What? A positive? Is that what we get? Yeah? Okay. So positive. What does that tell me about the graph? It's increasing. So where is this graph increasing? Everywhere on its domain, right? So this one's increasing from 1/2 to infinity, which is its entire domain. All right, second derivative information. That's my last step, right? Now, in terms of finding my second derivative, it'll be easiest if I use this part of my derivative notation where it's already written in the exponential form instead. So what will I get for my second derivative? It will be similar. It won't look exactly the same. Okay, so we're going to bring down the negative 1/2. We're going to rewrite the 2x minus 1. What's our new exponent here? It'll actually be a negative 3/2. And then we still have to do the derivative of the inside, which is 2. So as I simplify this, I still have that 1/2 and that 2 cancel, but there's a negative involved that wasn't really there before. So I have negative 1 over. And I don't actually have the square root down here. I could write this if I wanted with a square root. It would be the square root of 2x minus 1 to the power of 3. It's not going to really end up mattering because that's not really the goal of this question, right? It really isn't find the second derivative, simplify it to look nice. It really is to use the second derivative to do something. So if you leave that second derivative with the denominator looking like a power of 3/2, that's fine. It's not going to hurt anything. What am I supposed to do with the second derivative? Make it equal to 0. And what do we find out if that happens? It doesn't. It does not equal 0. The numerator doesn't. But we can find out where this does not exist. And it does not exist at, our magic number for this problem is 1/2, right? If I try to plug in 1/2, I get the denominator is 0. So we're going to do another number line. Our number line is going to have on it 1/2. I don't know why that's so thick. Let me try that again. So we have 1/2. What do you tell me about the values that are others on the left-hand side of 1/2? They don't exist. They're not in our domain, so we're not testing anything over there. We will test a value on the right-hand side of 1/2, maybe 1. We've tested it already. But we're going to test it this time in the second derivative. So what is f double prime of 1? In particular, is it positive or negative? It's actually a negative this time. So what does this negative tell me about the graph? It's concave down. So this graph is concave down where? Yeah, 1/2 to infinity. It's concave down everywhere on its domain. The entire graph is increasing and concave down. That's what that told us. Okay, so the graph for this one is pretty clean because I don't have a lot of different things going on. So that part's kind of nice. All right, so what do I need to include on this graph? The x-intercept, which is 1/2. So let me mark out just a couple of locations here so that I have some perspective. I don't have the grid like I did on the last slides. So if my x-intercept is 1/2, that's something like right here. Does that look okay? Roughly? Okay. And then what am I supposed to do as I move? What am I supposed to do on the left-hand side of that x-intercept? Nothing. What am I supposed to have on the right-hand side? Increasing and concave down. Okay, sketch what you think increasing and concave down would look like. Look at your neighbor's paper and make sure that yours and your neighbor's look similar. Do they? Okay, does everyone have a graph that looks something like this? Fabulous. All right, so just for fun, real quick, grab a calculator, put it in, and make sure that it resembles the graph that you have. What do we think? Does it work? Does it look similar? Excellent. All right, that is really what we're doing in this section. All the same stuff that we've done before put together. I mean, that's really what it is. Okay?